Hello, and welcome to the lesson that connects integrals, sums, and limits all together. Leibniz's integral rule tells us what to do when we need to take the derivative of this integral. Note that f is dependent of both x and t, while the integration is with respect to t. Also, note that the endpoints are functions of x as well. First, we move the derivative operator to the integrand. When taking the derivative with respect to x, we treat t as a constant. This is called a partial derivative, and we shall talk about it more in the multivariable calculus module. The upper endpoint gives us this term, and similar for the lower endpoint with an opposite sign. Notice that when f is a function only of t, alpha is constant and beta is x, we get the fundamental theorem of the calculus. Take this function, for example. Apply the Leibniz rule and plug in 1 to get the answer. This is a simple example, and you can calculate the integral directly and get an explicit function for capital F and its derivative. Go ahead and do that. Make sure that you get the same result. We define an integral with infinity as one of the endpoints as a limit of regular integral on finite intervals, which are getting bigger and bigger. This is one type of an improper integral. Another type is when the function is unbounded, so the upper Darboux sum diverges. Instead, we define this improper integral as a limit of these regular integrals, which are defined on intervals where the function is bounded. In most cases, we calculate the antiderivative and then calculate the limit on this antiderivative. We will see some examples for other cases. This is the basic example for an integral at infinity. When f is x to the power of p, and p is strictly less than 1, we get a monotone function for which the integral converges. This is because the antiderivative obtains a finite limit at infinity. In other cases, including p equals -1, the integral diverges. The function simply does not get close enough and fast enough to the x-axis. Classic examples for a convergent integral of unbounded functions is when f is x to the power of p and p is strictly bigger than -1. Of course, for a non-negative p, the function is even bounded. This is because the antiderivative obtains a finite limit at 0 for p bigger than -1. For other p's, including -1, the integral diverges. Recall the geometric series from the basic module. It converges for any x with absolute value less than 1. For example, for x equals 1/2, we get this convergent sum. Using that, we can build the following function composed of rectangles that are getting higher and higher, but also more narrow such that their area is 1/2 to the n. The integral for that function converges although the function is unbounded and does not obtain a limit at infinity. Remember this example. It serves as a counterexample in many problems. We can also smooth those rectangles and get the same features with a function which has derivatives of any order. Note that we can create this kind of function for every convergent series. Remember that the definition of an improper integral is for one problematic endpoint. When the two endpoints require an improper integral calculation, it must be done separately. If not, we might get weird results like that. The integral of x is 0 for any symmetric interval, but by definition, this integral is undefined. For this example, we have to divide the interval to 3 different limits.